Hi, this is class number 10 of week 10 assignments tutorial. Basically, you begin with question 1 as usual. That when a state vector psi transforms into another state vector psi prime by a unitary transformation, an operator a cap transforms as a cap prime. If a cap is Hermitian, then a cap prime is anti-Hermitian. You have to say that is true or false. So first of all, uh, let me go down. So it's a unitary transformation. So here psi is going to psi prime under that. So let's say u um, so psi is going to psi prime under a unitary transformation. That means if the matrix for the unitary transformation is u, then u a cap u dagger is equal to a cap prime, because this is the unitary transformation on the matrix A, right? Now it is said that A dagger is equal to A because it is mentioned in the problem that A is a Hermitian matrix. Then you take U A U dagger whole dagger is equal to your A prime dagger. If you want to see what is the adjoint matrix of A prime matrix, then you take the dagger sign and you take this. So you know that when taking dagger, this comes on the other way around. That means you reverse the order. So u cap dagger, dagger is u cap, then a cap dagger, and then again u cap dagger. So this is basically same as a b c whole dagger is equal to c dagger b dagger a dagger. So this is u cap, then a dagger is a, as you know that this is Hermitian, this is u cap dagger. So you are having, this is your basically unitary transformation operating on this a cap. So this is basically nothing but your a cap prime. So you are getting that a cap prime dagger is same as a cap prime. That means a cap prime operator is a Hermitian matrix, not anti-Hermitian. So the statement that is made in the question was that it was anti-Hermitian is a false statement. Actually this is Hermitian. So this is option number B is correct. Now question 2 is that the wave function of an electron in hydrogen-like atom is psi r is equal to c e to the power minus r by a, where a is equal to a naught by z and a naught is the Bohr radius. Then the normalization constant c will be what value? So first of all, this is a wave function, only radial part is given and you have to normalize it to see what is the normalization constant value, but you also have to take the other coordinates like theta and phi. So basically you have the normalization condition of the wave function. So you have psi r whole mod square d cube r, this is equal to 1. So d cube r is a volume integral which in the spherical coordinates you can break it down as r square sine theta dr d theta d phi is equal to 1, where there is a different integral limits for both all r, theta and phi. So if you take the different variables separately, like psi r, the expression was given as c e to the power minus r by a. So that is only a function of r. So then psi r whole mod square is basically c e to the power of minus 2r by a, and then r square is there and dr is there. So r here goes from 0 to infinity. And then for theta part you have sine theta d theta, where theta goes from 0 to pi, and for phi you have from phi equal to 0 to 2 pi, that whole thing is equal to 1. So then you have c whole mod squared, and then you have r square e to the power of minus 2r by a dr, r equal to from 0 to infinity. Then sine theta d theta is basically minus cos theta going from 0 to pi. So here you can take your 2r by a as y, then your r becomes a by 2 y, and dr becomes a by 2 dy. So here it becomes y equal to from 0 to infinity a squared by 4 y squared e to the power of minus y a by 2 dy, and this is cos 0 minus cos pi, which is plus 1 minus minus 1, which is plus 2 into 2 pi equal to 1. So you have c whole mod square into aq by 8 into 4 pi y square e to the power of minus y dy, where y goes from 0 to infinity equal to 1. So here you have c whole mod square into aq into pi divided by 2 into, this is a gamma function form where e to the power minus y and y to the power n means gamma n plus 1 or gamma 3 basically, which is equal to 1, which is c whole mod squared into aq pi by 2, gamma 3 is 2 factorial, which is 1. So this 2 and 2 cancels out, so c whole mod square is equal to 1 by pi a cube, or in other words c is equal to 1 by root over of pi a cube. So this is the formula. So you have c is equal to 1 by root over pi a cube. Option C is correct. Now the third question is, eigenstate of jx with the eigenvalue h cut by 2 will be which of these options? So you can see very well that even if the eigenvalue is h cut by 2, so initially you would have assumed that it is a spin half particle problem, but actually the wave function or the state is given like a 4 cross 1 matrix, column matrix. So here you can understand this is a j equal to 3 by 2 spin particle case, because only then you have like a matrix instead of 2 cross 1, you are having the state as 4 cross 1, because the clear understanding is that for if it is a spin half problem, for spin half particle you have you have then 2 cross 1 column matrix as your state vector, which is represented as psi k is equal to just a and b. Why? Because then you have only two values of m possible, which is plus minus half, right? So only two values, that is why 2 cross 1 matrix. But in this case you have 4 cross 1 matrix, that means 4 cross 1 psi is written as a, B, C and D. So there are 4 values of m can be there. That means mj can have 4 values, like so mj can only be 4, but that is when 2j plus 1 equal to 4. So basically you know that for if the spin is j, then there can be 2j plus 1 number of possible mj values. So that is if 2j plus 1 is 4, then 2j is 3 and j equal to 3 by 2. So your j value is 3 by 2. Then you have mj as minus 3 by 2, minus half, plus half and plus 3 by 2. So these are the 4 values, right? So you understand that this is j equal to 3 by 2 kind of a particle problem, a spin problem. So then you have to know that what is the eigenstate of jx with the eigenvalue h cut by 2. So for that you have to get what is the expression of jx cap, this matrix, what is the matrix form for this operator for such a case where the wave function or the state is itself in a 4 cross 1 matrix. Once you know the matrix, then you multiply with this eigenfunction and you can get the eigenvalue, and from there you can get each of the terms of that eigenfunction. So it will be a bit longer, but it is not always possible to memorize the form of j x in this case, what is the matrix form. So I will be deriving that to you, so how to get the jx matrix form, so that you do not have to memorize the jx form here, of course. So let us start that. It can be a bit lengthy, so just hang in there. So as I said that this is a j equal to 3 by 2 kind of a problem. So this is a j equal to 3 by 2 case where there are mj values, four values are there: minus 3 by 2, minus half, plus 3 by 2. Now how to write your J-cap matrix, J-cap operator form, how to write that? So the basic matrix elements will be like something like J m prime J m, right? So m prime and m are different values of m, j remains the same when you take the inner product. So each of the matrix element will be defined like that. So you have m around this m kit, and you have m prime bra around this column wise. So then there are four possible, because this will be a 4 cross 4 matrix as expected, because the column vector is a 4 cross 1 vector. So this will be like a 4 cross 4 matrix. So each of these matrix form will be m prime m will be the elements of the matrix, where all of the possible combination of m prime and m will be there. So first of all, for m values, let us write down the m. The m starts from, let's say, minus t by 2, minus half, plus 3 by 2. Similarly, for m prime, you have starting with minus 3 by 2, minus half, plus 3 by 2. So in the first case, you have minus 3 by 2, minus 3 by 2 as the inner product coming in the matrix element. So basically, you have now this is not the only question, but you have to also know what is the form of J-cap, right? Only after that you can write it down in a matrix element form like that. So J-cap is how to write that easily. So this is J plus J minus divided by 2, because if these are the like ladder operators, then J plus equal to simply, you know, Jx plus I Jy, and J minus equal to Jx minus I Jy. So from here you can get that Jx equal to J plus J minus by 2. And then you know J plus, when it acts on Jm, you will be having root over of J into J plus 1 minus M into M plus 1, then J m plus 1. So because it is a ladder operator in the plus end, so it takes the m to m plus 1 and with the former part like this with the h cut, because this is kind of a h cut will be included. Now if you have a ladder operator with a minus sign, then everything will be the same except this m plus 1 will be a minus 1 in this previous case. Okay, so these are the ladder operator form that you should be knowing. Now Jm prime, Jx, Jm, how to write that? So you have to use the Jx form in terms of the ladder operator. So this is Jm prime h cut root over of J, sorry, so let me write down the ladder operator first. So I have to use the eraser. Okay, so this is, you are writing as J plus J minus by 2 J, right? Then you have two parts. So half J m prime, you deal with J plus, and you also deal with J m prime, J minus, J m. So now you have known this form. So you know the h card will be coming common, so you take it outside, and this J plus will be root over of J plus 1 minus m plus 1, and then you have your Jm prime, Jm becomes Jm plus 1. So this is Jm prime, Jm plus 1 inner product, plus for J minus you have J to j plus 1 minus m into m minus 1, then j m prime j m minus 1. So this is the case. Now you know that this is like a Kronecker delta form will be there, because this inner product will only be non-zero if m prime is m plus 1, and for rest of the values this will be orthogonal, so this will become 0. So you have j plus 1 minus m plus 1 delta m prime m plus 1. So this is a Kronecker delta, you know the meaning. J plus 1 minus m minus 1 Kronecker delta m prime m minus 1. So this Kronecker delta means that it is only equal to 1 if m prime is the neighboring side m plus 1 and equal to 0 for all otherwise this. Similarly, this Kronecker delta means this is equal to 1 if only m prime equal to m minus 1 equal to 0 for else everything. So thus you know that this is a Kronecker delta representation, and from here you can know what are your matrix elements, because now you have h cut by 2 in common. You have this part where a matrix element j m prime with jm will only give you a non-zero value if it is either m prime equal to m plus 1 or m prime equal to m minus 1. So this is not equal to 0 only if m prime equal to m plus 1 or m minus 1 in the matrix element choosing of jm prime jx matrix of jm. So only out of this where m prime equal to either m plus 1 or minus 1, the value of the element will be non-zero, otherwise it will be all 0. So now we can map it out that for, let's say, first of all m prime and m combination is minus 3 by 2 minus 3 by 2. That means m prime equal to m. So whatever the element is, so this is j x minus 3 by 2 minus 3 by 2, so this will be 0, right? So I'll not be writing down everything, just I'll be telling you how whatever part will be 0 and whatever will be not. So this will be 0 because m prime equal to m. Now for the next case, m prime is minus 3 by 2 and m is equal to minus half, right? Now you can map it out also that when will be the case for m plus 1 and when will be the case for m minus 1. So for m prime m plus 1 for this j plus case, and the other case is j minus where m prime m minus 1. So in this case the options are m prime to have non-zero, you need m prime equal to m plus 1. That means you need to have m equal to m prime comma m equal to, the possible options are minus half minus 3 by 2, because m equal to 3 by 2 plus 1 is equal to minus half, or you can have plus half minus half, because again minus half plus 1 is plus half, or you can have 3 by 2 half. So these are the options. And similarly j minus is delta m prime m minus 1, this will be non-zero only when m prime equal to m minus 1. That means the possible combinations of m prime or n m will be so this will be like minus half plus half, so just the reverse sign of this, or minus 3 by 2 minus half, or half 3 by 2. So just the reverse of this will be this. So now you can choose in what case you are getting what. Also the prefactor for this case where m prime equal to m plus 1 is valid for j into j plus 1 minus m into m plus 1. So here the prefactor is this, and in this second case the prefactor where m prime is equal to m minus 1 is root over of j plus 1 minus m into m minus 1. So now mapping out, when m prime equal to m, the first term is 0. Now m prime 3 minus 3 by 2, m is minus half. So whatever combination is valid, you need to check from here. Minus 3 by 2 and minus half is this. So here j minus will be acting because m prime is minus 3 by 2 and m is minus half. So this is non-zero, but here it will be acting by j minus. So I am not, the matrix element is not j minus, but the operator that will be effective here is j minus. So I am writing j minus in short. So this is just for our understanding. This is not the actual matrix element, you have to remember. So you have to calculate the matrix element using j minus. Now for the third case, you have m prime minus 3 by 2 and m as half. So no such combinations are present here. So this will be definitely 0. Now last case, you have minus 3 by 2 plus 3 by 2. Also no such combination is present like that. So this will also be 0. So minus, so 0, j prime operation, j minus operates, and then 0 0. Then when m prime equal to minus half and m equal to minus 3 by 2, your combination acts as this combination, so which is operated by j plus. So here you have to effectively take j plus. Then minus half will be 0. Minus half plus half is out of these four options. These, so this is j minus effective. So this is j minus. Then minus half 3 by 2 is no combination, so 0. Then half minus 3 by 2 is also no combination, 0. Half minus half is, you can see that this is half minus half is this. So this is j plus of effective. Then half is no combination, 0. Half 3 by 2 is this combination, which is j minus. So it is affected by, it is controlled by j minus. Then 3 by 2 minus 3 by 2, no combination, 0. 3 by 2 minus half, also no combination, 0. 3 by 2 half is this combination by j plus. So this is j plus. And then 3 by 2, no combination, 0. So the matrix element has been simplified a lot, to a lot extent. So you can further write it down as Jx cap matrix is, can be written down as 0 operating by j minus, 0 0, j plus, 0, j minus, 0 0, j plus, 0, j minus, 0 0, j plus, 0. Now this is your form. Now wherever you have j plus, you have to operate the element by acting j plus. So what is in the first case, j minus is this m prime j minus m is, here m prime was minus 3 by 2 and m was minus half. So this is, so m equal to minus half is only thing that you need out here. So as a free factor, you know that this is h cut. Root over of j is plus half always. So j is equal to 3 by 2. J into j plus 1 is 3 by 2, 3 by 2 plus 1. Minus m into m minus 1 is minus half into minus half minus 1. Which is like h cut root over of 3 by 2 into 5 by 2 minus minus plus and again minus. So this is 3 by 2 into half is 3 by 4, which is h cut 15 minus 3 by 4, which is 12 by 4, which is h cut root over of 3. So here the element is root over of 3. Now you have j plus, and here the m factor is m equal to minus 3 by 2, because only the m value is needed in the free factor. So for this case, so this was for this case. Now for this case, you can take the prefactor is, for m equal to is, here m equal to is minus 3 by 2. So m equal to minus 3 by 2. Then the prefactor is root over of j into j plus 1 is 3 by 2, 3 by 2 plus 1 minus j plus. So this is minus 3 by 2 minus 3 by 2 plus 1, because this is m plus 1. Right? So this is 15 by 4 minus 3 by 2 plus 1 is minus half. So minus plus and again minus. So this is 3 by 4 this is again root over of 3 you are getting. So now this j minus, here this j minus has m equal to plus half, right? So m equal to plus half. So the prefactor here for j minus is root over of j into j plus 1 minus m is plus half m minus 1, which is like root over of 15 by 4 minus minus and minus making it plus 1 by 4. So this is root over of 16 by 4, which is root over of 4, which is 2. Okay. And now similarly this j plus, this has m as minus half. So you can so I'll not show the rest of the things because these are pretty similar manner. Just you have to take each of this matrix element and calculate whether j plus prefactor will be effective or j minus prefactor will be effective, and for that you only have to take note of this m value, right? Because that is effective in the formula. Now we can do the rest of this, like this and this, which I have left for you. You can choose it, choose to do that for yourself, and then finally when you solve all of them, you can replace it in the main matrix form. And like here you got j minus operating, you have root over 3, and remember with all the terms you have h cut because h cut is present with the prefactor, so do not miss out on h cut. So this is h cut is present everywhere, so you can take h cut as common, right? Then this is 0, this is giving you root over of 3, so 0 root over 3 0 0. Then you have again you got root over 3 here, and this you got as 2, so this is root over 3 0 2 0. Then on this term if you solve, you will get here there will be a 2, and then the last term there will be a root over 3, and then for the last row you have 0 0 root over 3 0, right? And also another thing is that you have basically you have a half factor also missing because you had j plus j minus by 2, so there is a half factor present. So not only j plus or j minus, but also half factor will be there. So by that, so this is, there is an h cut by 2 present, so don't only write h cut, but it is h cut by 2. So thus you have obtained the 4 cross 4 matrix form of jx for this case. Now you can easily form an eigenvalue equation jx as a b c d is equal to some eigenvalue which was mentioned in the question as plus h cut by 2. So this plus h cut by 2 a b c d. Now this h cut by 2 and the jx has another h cut by 2, so this is 0 root over 3 0 0 root over 3 0 2 0 0 2 0 root over of 3 and 0 0 root over 3 0. So this is equal to, so this multiply with a b c and d, so this is h cut by 2 a b c d. So this and this cancels out, so you obtain root over 3b, then root over 3a plus 2c, then you have 2b plus root over 3d, then you have root over 3c. So this is giving you a b c d. So from comparing you get a is equal to root over 3b, or your b equal to a by root over 3. Similarly your d is equal to c into root over 3. In the second term you have root over 3a plus 2c equal to b, and b is, you know that, a by root over 3. Then you have 2c is equal to a by root over 3 minus root over 3a, which is like a minus 3a by root over 3, which is minus 2a by root over 3. So you get c equal to minus a by root over 3. And then you get a d equal to minus a by root over 3 into root over 3, which is minus a. So by assembling all parts you have a b c d, and you have a written as a, b is equal to a by root over 3, c equal to minus a by root over 3, and d equal to minus a. Now you can take minus a as common, You can also take a as common, but I am taking minus a as common to match the answer, because you see that both are equivalent. Whether you take 1 as common or minus 1 as common does not matter. This is an equivalent state, so you can take minus a as common from all of this, because that is just a prefactor which is common in all of them, so you can take that out. Similarly, you can take minus 1 common from all of them out, so you get minus 1 by root over 3. This becomes plus 1 by root over 3 and plus 1. So now let us match our answer with the options given to us. So this is our option. And also you see that there is a prefactor we have missed also, because 1 by root over 2 will be there because we have missed normalizing it. So normalization is an important factor, otherwise it will not be eligible to be called as an eigenvector. So you have to not miss the normalization. So normalization for A, B, C, D, this vector Kate is A squared plus B squared plus C squared plus D squared is equal to 1. So you have 1 plus 1/3 plus 1/3 plus 1 with an additional prefactor of, let's say, whatever you call the prefactor. Let's say your normalization factor is m naught. So m naught square, this thing is equal to 1. So m naught squared is equal to 1 divided by, this is 2 plus 2 by 3. So 2 plus 2 by 3, 8 by 3. So this is 1 by 8 by 3 is equal to 3 by 8. That means m naught is equal to root over of 3 by 8. So here you have the normalization factor after normalization is 1 by m naught, that is 1 by root over of 3 by 8. Sorry, 1 by root, sorry, not 1 by root over 3 by 8. Basically m naught is a normalization factor, so m naught times a, b, c, d is your normalized eigengate, equal to this, so equal to root over of 3 by 8. A, B, C, D is basically uh, sorry, A, B, C, D is basically minus 1 minus 1 by root over 3 plus 1 by root over 3 plus 1. So this is 1 by root over of 8 minus root over 3 minus 1 plus 1 plus root over 3. So this is your answer. This is option number C you will have. So just we missed a normalization factor, and because of that so sorry, I marked the wrong answer. This is not 1 by root over 2, this is 1 by root over 8. Sorry, again wrong answer. Very sorry. So let us 1 by root over 8 and then first two are the minus sign. So our correct answer will be option number A, which is also the correct answer. So this is not the correct answer that I wrote down by mistake. So this is the answer we have obtained. So finally we have obtained. Now question number 4, consider an operator O cap is equal to I j x cap j y cap, then the expectation value of this operator for j equal to m equal to half is how much? So j x j y has a product and you have to take the expectation value of O cap. Now for simplification sake, so let us check. Question number 4 is O cap is equal to I, this is imaginary I, j x cap j y cap. Now O cap expectation value is Jm, you have to take Jm is equal to I. Now you know that Jx equal to J plus plus J minus by 2 and Jy equal to J plus minus J minus by 2I. This is 1 by 4I J plus J minus. Now these are operators, so these are not simple products, so you have to maintain the order. So 1 by 4I, then J plus J plus plus J plus, sorry, this is minus J plus J minus then plus j minus j plus, then minus j minus j minus. So you have so you know whatever action is of j plus on a state Jm, there is a free factor. This I have also written down just in the question earlier. So I am again writing it down, minus m into m plus 1. This makes it ladder operator j m plus 1. And j minus will be m minus 1, m minus 1. So in this case, when you have j minus j plus acting on jm with jm, you have jm some j plus some prefactor j m plus 1, and then again you have, sorry, this is j m minus 1, which is the prefactor. You take it out as j into j plus 1 minus m into m minus 1. Then rest of the term is j plus j m minus 1. So this factor is there, minus m minus 1. When j plus acts on j m minus 1, so the new m is m minus 1 basically. So it has to take the j plus prefactor. So j into j plus 1 minus, instead of m into m plus 1, you have now m prime as m minus 1. So this is m is now m minus 1 effectively. So this is the thing as prefactor. Again, because this is a ladder operator with plus, so m minus 1 becomes m, right? So this becomes m. So this j plus has already operated. So this is jm inner product. So this is root over of j into j plus 1 minus m into m minus 1 into root over of j into j plus 1 minus m into m minus 1. So this is whole squared. So there is also h cut. So another h cut and h cut. So this is h cut squared. So this is j into j plus 1 minus m into m minus 1. There is a square root has been squared. So this is h cut squared. And this is equal to 1 because that is orthonormal. So they are also normalized. Similarly, you can calculate what is jm with j minus j plus, and you can see that this becomes jm j minus root over of j plus 1 minus m plus 1 into h cut j m plus 1. Let us draw a boundary here. So this constant term comes outside j plus 1 minus m plus 1 with an h cut, and then jm when it acts on j minus, when it acts on that, so this is root over of j into j plus 1 minus, so this is a j minus, so this is m plus 1, then m plus 1 minus 1, right? Because now the effective m is m plus 1. So that is why you get this. Now j m plus 1 becomes again j m because this is j minus. Now you have also an h cut. So this is h cut squared. Now you have j into j plus 1 minus m into m plus 1. Square root has been taken a square. So this is simply without any square root. And jm is 1. So this is just h cut squared. J into j plus 1 minus m into m plus 1. But the rest of the terms will be giving you 0. That is very easy to guess because j plus acting twice. So j plus first initially operates and takes jm to jm plus 1, and when it again operates, so it takes m plus 1 to m plus 2. So that is why you have an inner product of, with whatever excluding all the prefactors, you have an inner product of jm state with jm plus 2 state. Now m and m plus 2, they will be orthogonal to each other, so this will be 0. Similarly, for this term, you have, in excluding all the prefactors, you have jm going to j minus 2 by this double j minus operator, and m and m minus 2 are different, so their orthogonal product will be 0. That is why only these two terms are effectively surviving and contributing in a non-zero value. So this is equal to 1 by 4i is the term here, and there is another I from imaginary, so this I and I cancels out, and you have minus j plus j minus. So this, with this prefactor, has a minus sign, so this is minus j plus 1 plus m into m minus 1. Each card square is taken as common, and then a j minus j plus has a plus sign, so that is j into j plus 1 minus m into m plus 1. So this is plus j into j plus 1 minus m into m plus 1. So this is the case, then this is just all of the rest of the terms will be 0, only this is 1. So j into j plus 1 minus j into j plus 1 cancels out, and you are only left with 1 by 4 each cut squared. This is m squared minus m squared minus m. This is also cancelling out, so this is minus 2m each cut square by 4. So this is minus half m each cut square. Now in the question it is written down that what will be the value for m equal to half. So if m equal to half, this is half into half with a minus sign each cut square. This is minus each cut square by 4. So if this is your correct answer, you have to see the options. So minus h cut square 4 is the option answer we are getting. So this is minus h cut square by 4. D is the correct answer. So you are getting that. Now question number 5 is, if psi plus r and psi minus r are the eigenfunctions of the parity operator belonging to even and odd eigenstates respectively, then they are orthogonal. You have to say that is true or false. So for parity operator, you know the rule already, that if this is a parity operator P, and if acts on a state psi r, it will take it the state to psi of minus r. So it takes from r to minus r. Now if it is stated that psi plus and psi minus are the eigengates of the parity with even and odd parity, that means that here the eigenvalue for even parity is plus 1. Okay. And the even for the odd parity for psi minus r, the eigenvalue is minus 1. Right, because they are eigenvalue equations. So psi plus at r remains at r because it's the eigenvalue equation, we cannot change that. So only there is a even and odd parity, that is why the eigenvalue of the parity operator is plus 1 for even and minus 1 for odd. Now you have whether you have to say whether they are orthogonal or not. Psi plus and psi minus orthogonality you need to check. That means psi plus and psi minus inner product you need to check. So this is the case, right? And now you have psi plus is nothing but your P operating on psi plus, and psi minus is nothing but minus P operating on psi minus. So this is as psi plus, then P when it comes to this side it becomes, to take the minus sign outside, P when comes to this side becomes P dagger, P psi minus. Now this is the property of parity operators, that P squared is I and P dagger is equal to P. So in that case P dagger P is equal to P into P is equal to P squared is equal to I. You can derive it by yourself. This is already done in previous lectures where we first learned about these operators. So I am not again deriving that. You can do it for yourself or check the textbook how you are getting that. But essentially you are finally getting P dagger P is equal to an identity matrix. So this is I. So this is minus psi plus and psi minus. So this is psi plus I minus inner product is minus the same inner product. So this is like saying A equal to minus A, which is not true or not possible, but only possible only if A equal to 0. That means the only option is psi plus and psi minus inner product is 0. That means So they are orthogonal. Now question number 6 is an electron of mass m and charge minus e moves in a region where the uniform magnetic field B equal to curl of A exists in the z direction. The Hamiltonian operator of the system can be written as what? So one second. So an electron of mass m and charge e, right? Charge minus e. Now you know the charge particle in a magnetic field kind of a problem. What? How does the Hamiltonian look like? You can directly say from that, but I'll be being more specific that under for like let me write down here only. So this is a problem, typical problem of a charged particle in a magnetic field B equal to curl of A. So here the momentum, which is the kinetic momentum, changes because of this vector potential. Kinetic momentum changes pi as pi vector is equal to p vector minus q a by c. 1 by c comes because when you take the series unit convention, and q is the charge of the particle. A vector is the vector potential. Now if your B is along z cap, then that is mentioned in the question that that is exists only in the z direction, then how can you, what can you talk about the value of A? So B equal to B z cap only is equal to curl of A. So this is x cap, y cap, z cap, del x, del y, del z, and curl of A. So divided into components ax, ay, az. So for z cap you only have del ay, del x minus del ax, del y. So here you have that del ay, del x equal to b. Let's assume, let's take, you can choose any of this. Let's, for simplicity, let's take ax equal to 0, and so then del ay del x minus this 0 equal to b, because both are z components, so this is just simply b. So in this case a y will be bx plus, you ignore the constant, so this is just plus bx. That means your a vector is ax, ay, az, and your az is also 0, chosen as 0. Only ay components are surviving, so this is 0 b into x into, and the third component is also 0. So a vector is a vector potential. Then your pi, that is a kinetic momentum, which is a measurable quantity, goes into p is the canonical momentum, p vector minus q is minus e in this case for electron, so this is plus e a by c. So for x direction you have pi x as px, because ax is 0, so this is 0, so this is just px. But for y you have pi y py plus e ay by c, but ay is not 0, ay is b times x, so this is py plus eb x by c. For z component, pi z equal to pz plus e az by c, but az is 0, so this is just pz. So thus you have pi x px, pi y how this is py, pi z how this is connected to pz. Then your Hamiltonian, which is basically your p squared by twice m if you ignore the potential energy part for all x, y and z. But because of the vector potential, or in the presence of the field in the y direction, the momentum has changed to kinetic measurable momentum and not the canonical momentum of p. So you have p x squared 1 by twice m in common, plus instead of py squared you have pi y squared plus p z squared. So this is 1 by twice m px squared plus py plus ebx by c whole squared plus pz squared. So this is your correct answer that we are obtaining. Now question number 7. Classically the rotational energy of a molecule is given by 2 pi squared I nu squared, where I is the moment of inertia of the molecule and nu is the number of revolution per second. Moving to quantum mechanics, in such a rigid diatomic molecule is it in the state L equal to 2, then the number of vibrations per second nu will be how much? So let us take the blank page again. This is question number 7. So for the classical case, the rotational kinetic energy is the only energy mentioned in the problem. So this is half I omega square is the rotational kinetic energy formula, which is given in the question as 2 pi squared I nu squared. So nu is basically the frequency or number of revolution per second. I is the moment of inertia which is present in both sides. So that is there. Now for this is the classical case, but to connect it with the quantum mechanics, so you can treat this rigid diatomic molecule as a rotor. As a quantum mechanical rotor, where the energy are L square divided by 2I. You know that is also true for classical case, because E is equal to generally for kinetic energy without any potential energy is P square by twice m. But for angular momentum case, P will be replaced by the angular momentum L, and instead of m you will have the mass will be represented by the equivalent moment of inertia for the rotational case, which is I. So this is the classical idea, you know that. But for quantum mechanical case, instead of L squared you have the expectation value of L squared operator divided by 2I. So this is this. So then you have because your Hamiltonian looks like this, so your energy expectation value is the expectation value of Hamiltonian. So Hamiltonian looks like L cap squared by 2I. So H cap, which is the energy eigenvalue, is the expectation value of H cap, which is L squared divided by 2I, which is L into L plus 1 L square is there. So basically L square eigenvalue, you know that this is L into L plus 1. So here it will be L into L plus 1 H cut square divided by 2 into I. This is the eigenvalue for the quantum mechanical case from this Hamiltonian operator. This is equal to, given in the classical case, that is 2 pi square I nu square. So this is 4 pi squared I squared nu squared is equal to L into L plus 1 H cut square. So this is I equal to, so L into L plus 1 is, L is given as 2, so L into L plus 1 is root over 2 plus 1. So this is root over 2 into 2 plus 1. Sorry, initially they are all powered by a squared form. So we are having, so this is L square by twice a in quantum mechanical eigenvalue form. You can write down L square eigenvalue as a into L plus 1 h cut square divided by 2I is equal to 2 pi square I nu square. This is 4 pi squared I square nu square is equal to L into L plus 1 h cut square. So then you have your nu, the rotational this revolution per second, or this frequency, is equal to root over of so if L value is given as 2 in the problem, so this is 2 into 2 plus 1 4 pi squared, then so you are having root over 2 into 2 plus 1 h cut divided by 4 pi squared. um, so this whole thing is under square root, so 4 pi squared 1 by nu root over into L plus 1 h cut divided by 4 pi square nu squared. So 4 pi squared 4 pi square into I. So this is root over of this. So this is root over of 6 2 this is root over 6 h cut divided by 4 pi square root is 2 pi into, so you are getting the answer as root over 6 h cut divided by 2 pi I. Okay, this is option number D, root over 6 h cut by 2 pi I. Now question number 8. The Hamiltonian operator is A dagger minus half. M equal to h cut equal to omega equal to 1. For simplification, it has taken as a dimensionless, where the criterion and annihilation operations are given as this. In the energy eigenfunction of this state is the quantum number related to this state is, so So this is A dagger, so A will be, so this is x plus ip into x minus ip. So this is I have just written down that this is a plus a dagger psi. So what is the form of a? So form of a is x plus ip by root over 2. Form of a price x minus ip by root over 2. So a dagger is equal to x plus ip into x minus ip by 2. So this is you are obtaining from the expressions given. Now p equal to, you know that this is minus I h cut del x, but since h cut equal to 1 has to be taken, then p is equal to minus I squared minus I plus I. So this is just x plus ip right. So we are here due to a technical glitch. So a dagger is equal to x plus ip and x minus ip divided by 2, because that is the form given in the uh, form of a and a dagger, right? And then because each card has been taken for simplification to be 1, so you know that what this form will be looking like. So this is like this will be like let me just check. So x squared minus I x, and then after that p is minus I del x plus I minus I del x of x, and minus and plus minus I squared is plus 1. Then px squared is um, I h cut whole squared, so again minus h cut square to del x2 divided by 2. So this is half x squared minus and minus plus, and then again I squared is minus 1. So this is minus x del x. I squared is minus 1, so this is plus del x x, then minus h cut square del 2 del x2. Now when this thing operates over uh, what do I say, so either that, or you can directly say when you operate this on your state psi, which is given in the question as 2x cube minus 3x into e to the power of minus x squared by 2, then you take each of this derivative and each of these terms separately and you solve term by term. So you see that d2 psi dx2 is equal to ddx of x squared minus 3 e to the power minus x squared by 2 plus 2x cube minus 3x e to the power minus x squared by 2 minus 2x by 2. So this is ddx of e to the power of minus x squared by 2, 6x squared minus 3, this is minus x, so this is minus 2x cube minus minus plus 3x squared. So this is ddx of the power minus x squared by 2, 4x cube plus 3x squared minus 3. So when you again take a derivative, this is 12x squared plus 6x e to the power minus x squared by 2 plus 4x cube plus 3x squared minus 3 e to the power minus x squared by 2 minus 2x by 2. This is e to the power minus x squared by 2, 12x squared plus 6x minus 4x to the power 4 minus 3x cube minus minus plus 3x. So which is like to the power minus x squared by 2 minus 4x to the power 4 minus 3x cube plus 12x squared plus 9x. Similarly, you can do the rest of the terms, like you multiply x with this thing and then take the derivative once. Then again you first take the derivative on this and then multiply by x, and then if you deal with all of these terms separately, which I am not showing you here, but if you do carefully all of these terms, then you will be ending up at a form like finally the form will be like where a dagger is operating. So a dagger on psi, a dagger on psi, when all the derivative and x these functions are done, so we'll be having half 16x cube minus 24x e to the power of minus x squared by 2, which is like half into 8 3x minus x squared by 2. So this is 4 2x cube minus 3x to the power minus x squared by 2. Now you know that this Hamiltonian operator is given as a dagger minus half. That means a dagger is equal to Hamiltonian plus half. So then a dagger acting on psi is basically Hamiltonian acting on psi plus this extra half. So you know this is a harmonic oscillator problem. So the eigenvalue of this Hamiltonian is n plus half. Now h cut omega, h cut equal to 1 and omega is equal to 1 given in the problem. So this is simply h cut half, omega will be 1 and n plus half will be there. So half this plus this. So this is n plus half psi, or you are getting this is equal to n plus 1 psi. Now or rather this is not psi, this is n basically, because it's the occupation number basis. So this is n plus 1 n ket. So what you are getting is that this is again the form of the state n or psi given to you. So this is 4n, which is like 3 plus 1 n ket. Okay, so if you compare this with this, because both are a dagger acting on psi, or in this case n, so this is the state n. So that means you are getting n plus 1 n ket equal to 3 plus 1 n ket, or you are getting n equal to 3. That means your value of n will be 3, which was asked in this question. If you look at it again, so you are asked that whether the quantum number associated with state is at n equal to what? So n equal to 3 is the answer. Now question number 9 is, if x prime and uh, px prime are the coordinate and the momentum after time reversal, then the fundamental commutation relation of x prime and px prime will be what? So you know that before time reversal, x and px has this commutation relation of plus I h cut. Now x prime under time reversal, tx t dagger has become x prime. So under time reversal, no change of position happens, so x prime is equal to x, remains x. But under time reversal, the momentum changes its sign, so px prime is actually minus px. So your px prime, x prime px prime is equal to actually x minus px. So this is the minus of x px, which is minus I h cut. So this is true. Now question 10 is, this is question 9, and question 10 is the value of 10 j square jz 10. So this you can derive it right here, that 10 j plus square jz 10, right? Okay, so then you have 10 j plus square jz commutation relation bracket is j plus square jz minus jz j plus square 10. So here 10 is equal to L and M, so L equal to 1 and M equal to 0. Now these are eigenstate for j squared, j plus squared is basically j plus acting twice on 10. So this is equal to root over of h cut j into j plus 1, so 1 into 1 plus 1 minus m into m plus 1, so this is 0. This becomes 1 1 because this is a ladder operator. Now this has to be acting twice, so this is another j plus, so this is h cut squared. This was root over of 2 earlier. Now your j is again 1 into 1 plus 1 minus m is 1 into 1 plus 1, m plus 1. So this is 1 2 because it is now m plus 2. So this is root over 2. This is 2 minus 2, so this is 0. This is 0. So j plus squared acting on this is already 0. That means this part, second part will be 0 already. Now jz acting on 10 will be m h cut 10, which is m is 0, so this is also 0. So both of the terms is giving you 0, so the final answer will be 0. So the answer is 0, which is the correct answer. So with this we have also solved this class 10 or week 10's assignment problems. We'll be discussing next week in the next tutorial.